Hello, welcome back to another lecture. I hope you're well. We're going to continue with load and load path. We did dead load, life load, and we are going to go ahead and proceed with snow load. Now, I'm not going to go over explain this snow load. I'm just going to give an example, and we're going to follow the example step by step. That's the easiest way. We're just going to go ahead and follow the code. Just pause the video for a little bit, go take a look at section 7 of ASCE for 20 minutes and then come back. And while you're there for 20 minutes, don't fall asleep. I know it's going to be tiresome a little bit. But it's good to just look at it, familiarize yourself with that chapter 7. And after you finish that, come back and do about 20-30 push-ups. If you can beat my push-up challenge, then you kind of waken up a little bit, and we're going to go ahead and do this problem. This problem is a little bit more steps than the previous problem. So go ahead and take a look at the board where we have for the problem. And we have this building right here. And it says calculate the snow load for one-story warehouse. The warehouse building roof slope is 1/2 inch on a foot. And you see the building is about 20 feet tall, and then you have the slope is 1/2 inch per foot, and you got the column and the layout from above, and it's 256 by 148. Okay, what we're gonna do, we're just gonna go ahead and go use the code to solve this, and take a look at what I have for the procedure. We're gonna go ahead to calculate the snow load. We're gonna use this 10 steps, which is it's first find the ground snow load, and all the way to step 10, consider the existing roof. I'm not gonna read all 10 of them, but as we go along one by one, we're gonna explore it. So take a look at the problem again. There it is, and let's go to one of the things given with this problem is the location is at St. Louis, Missouri. The surface roughness category is given as a C, and there's obstruction less than 30 feet high. Occupancy is a warehouse use with less than 300 people. Okay, we have the thermal condition. Structural is kept just above freezing, and a roof exposure condition partially exposed. We need those information, and a roof framing. Okay, so let's proceed with the step number 1. Step number 1, it says load calculation, determine the ground snow load PG, and normally you can find these from local codes, and that's the best way to find it. Every local code, every state has one of these. It can tell you exactly what town and what is the ground snow load is. And if you can't find that, then you can go ahead and go to either IBC or ASCE figure 7.1, and for example here they have the region for United States, and you can pull in the ground snow load off the map. And for our problem, it comes out to 20 pound per square foot. So let's start out and say, okay, our PG based on a map or based on a local comes out to 20 pound square foot. Okay, we got one done. Let's go to step number 2. So we had step number 2 is determine the roof, the flat roof snow load PF. Okay, flat roof snow load PF, and again, that's gonna be there's a formula there in that equation. If you take a look at the ASCE 7.2, we see that PF is equal 0.7 CE CTIS CTI and then PG. Okay, and we already know the PG. So we're going to go ahead and find the rest of those. We're going to find CE and CT and I, and those are step by step. And when we go into table 7.2 exposure factor CE, and from that table we knew from the given the problem, the CE, excuse me, the terrain category was a C, and our thing was partially exposed, so our CE comes out to equal 1. Okay, so this kind of come out to PF is equal 0.7 times 1. And then the next item is a CT. And if you look at the 7.3 CE right there with the formula and look for CT, the value of CT shall be determined from table 7.73. So when we go to 7.3, we can see that our CT comes out 1.1 because the structure kept just above freezing and others with cold ventilation. So we're going to fit in that category, so it's going to be time 1.1 right there. And let's find the important factor. And that's the last one left. And the important factor is, before you find important factor, you have to take a look at table 1.51 to get the risk category for the building, because you need that to find important factor. So the risk category for the building is the type 2, risk category 2, because, and as you can see right, it says all building and other structures except those listed in risk category 1, 3, and 5. You can still read them, those other one yourself, but this comes out to risk category 2. Now you have that, you go to a table 1.52 to find the importance factor. And the important factor, it comes out to be 1 because, as you see, is a risk category 2, and we're looking for snow, so that is 1. Time 1, and our PG was 20. And therefore our PF comes out to 0.7 times 1 times 1.1 times 1 times 20, 15.4. 15.4 pound square foot. Okay. Now look at the section 7.34. It says right here, this is highlighted, minimum slow load for a low slope roof. And we might have to, where PG is 20 pound or less, then we have to use this formula here. And we got to find out first of all if we're going to meet this criteria. So the slope has to be less than 15 degree. And let's find the slope of our roof. The slope of our roof is going to be, it says right here we have ½ inch, 12 inch. So let's find the angle. The angle that comes out to, you know, that from London, from a kindergarten. Tangent said this is alpha is equal ½ inch divided by 12, and inverse tangent. So you figure out alpha comes out to, I call it alpha, you can call it whatever, 2.3 degree. And that's less than 15 degree, what the specs call for right there. Therefore, it says if it's less than 50 degree, PG is equal 20. Yep. The minimum snow load for a low slope roof shall be obtained using the following formula. And it's got to be PM, which is equal 20 times IS. 20 times IS, and IS came out to 1, and therefore that comes out to 20. So that was step number 2 or 3. 2. Okay. Step 1, step 2. Let's go to step number 3. So step 3, it says find the slope roof snow load PS. And a formula given for PS, let me use a different color here. So step 3, and we have PS is equal CS PF, which you have already calculated. So we got to go ahead and find where is CS. A CT is equal 1.1, and our CT was 1.1. So therefore, that's where we are, and we're going to use the table 7.3, 72B, sorry. We're going to use table 7.2B, and when you look at the table right here, you go all the way up to the corner where I have highlighted, because our roof degree is less than 10 degree, so therefore our CS comes out equal 1. So CS is equal 1, and therefore our PS is equal 1 time what we had, 15.4. 15.4, so it comes out to 15.4 pounds square foot. So this is the, right now what we have right here, this 15.4, this is the balanced snow load for the roof. It's the what we have. Now let's go to the step number 4. Step number 4 says consider partial loading. And when you read the spec right here, because of all our member at the beginning of the problem mentioned that everything is simply supported, so we're not going to worry about partial loading. And therefore, let's move on to the next step. So, okay, so this will bring us to step number 5, which is kind of interesting. Step number 5, it says, consider balanced snow load. Unbalanced snow load. So our snow load is unbalanced. Why? Because if you read the spec on 7.6.1, unbalanced snow load for hip and gable roof, it says has to be less than 2.38, which is half inch and 12 inch, where our slope is just exactly half inch and 12 inch. Therefore, we have to investigate unbalanced. We say yes. And then it says that W has to be bigger than 20 feet. And our W says, the length of our building came out to be 256 divided by 2, which is 128. That's bigger than 20. So, okay, now we unbalanced. That's good. And the next step, we're going to go ahead and we look at it. Is if you look at the highlighted area, we're going to calculate the unbalanced load on a windward and on a leeward side, and also on a drift side. And it says for windward side is 0.3 PS. So let's come over here for windward side. Windward side is 0.3 PS, and that's 0.3 time we had 15.4 over there. So that comes out to 4.6 pound square foot. So that's the windward side. Let's go to the leeward side based on that spec. Okay, I dropped my ruler, it's okay. So leeward side is, there's an equation for it. It says it's a PS plus. So we have a PS, which is a PS, and PS came out to 15.4. Okay, now, and then it says plus rectangular surcharge with a magnitude of HD gamma divided by, that's plus HD gamma divided by square root of S. Now we got to figure this out. What is HD? What is gamma? What is S? So we're going to go ahead and figure it out. And continuing with the what I have on screen on the next page, look at that. It says HD is equal 0.43. Let's write that formula down. HD is equal 0.43 time LU by power 1/3, and then time PG plus 10 by power 1/4, and then minus 1.5. Okay, So we got to figure out HD. LU is the same as 128. So LU is 128. That's the same as a W divided by 2. I mean, W itself. And what else I need? PG we know it was 20. And let's figure this out then. So plug that in, it's going to come out to 0.43 multiplied by 128 by power 1/3 and multiplied by 20 plus 10 by power 1/4 minus 1.5, and that comes out to I have 3.6. Double check my calculation. Okay, so 3.6. So now we got this part. We got to find gamma. And when we go look at the spec says right here gamma has to be equal 0.1. Gamma is equal 0.13 time PS plus 14. PG plus 14 was a PS. PG 20. Okay, so it's 0.13 times 20 plus 14, and we get 16.6. And the unit for that is a pound cubic foot. It says it has to be not more than 30. So we less than 30, we good. Okay. And then let's go find S. What is S? S is basically if I have a roof like this, all right, and normally the pitch is like that. They call this S, but this has to be 1. So it's 1 on what? If I got 1/2 inch on 12, therefore I got 1 on, you read it, that's right, 24. 1 on 24, so S is 24. And now I'm going to come back and calculate this, and this become HD 3.6 time gamma was 16.6 divided by square root of, where'd it go, 24. And therefore this comes out to, what do I have? I end up with, it's in the other page, 12.2. 12.2 pound per square foot. Okay, now remember the spec says we found this has been our roof right here. And let's go back, put the shape on here, right there. If you have the roof, this side was the leeward, windward, and this side was the leeward right here. Now we want to find out our load. So we found basically I need room. Let me erase this to explain this here. Okay, so if this being our roof, it's not quite exactly drawn. I'm gonna have my uniform load right here. This was the balance load, which we already calculated. That came out, what was that, 4.6 pound per square foot. Where was that? Right there. So this is the balance load. For the other side, for the unbalanced load, on the other side, we had 15.4 plus. So now we have 15.4. This from here to the center be right here. That's right here is, okay, so 15.4 from bottom to top right there. And so this is 15.4. Remember we had plus right here. And then plus the rectangular section. The rectangular section is going to be right here. Okay. I want to know what this width is right now, which I don't know. And the magnitude we found for this came out to be right here, 12.2. So that's 12.2 right there. And that's on top of that. But let's find out W. The W comes out, if you look at the equation right here on the board, the W comes out to a 3.8 multiplied by HD, which HD came out to HD 12.2. Okay. And multiply by square root of 24. 24, and that should come out to 47 feet. So this is 47 feet. And we know this whole distance right here is 128. All right, that was step number 5. Let's move on to step number 6. Of course, I need room. I'm going to erase that side and work back that way, and give me a few minutes. All right, let's move on to step number 6. And step number 6 is, let me put on a board here. Consider a snowdrift on a lower roof. We don't have a lower roof, so that does not apply. Consider sliding snow. That does not apply either. And let's move on to step number 8. Consider rain on snow load. Oh yeah, that will apply. So we go look at the spec. The spec right here says, for location where PG is 20 pound per square foot or 0.96 kilonewton per meter square or less, but not 0, all roof with a slope in degree less than W divided by 50, with W being in feet, and they give you the SI formula also, shall include additional 5 pounds. So W divided by 50 is equal 128 divided by 50, and that is 2.56. Okay, 2.56, it says in degree. And 2.56 is bigger than what we had, 2.38. All right. So that means, okay, we got to add additional 5 pound to the additional 5 pound per square foot for the rain. So it's going to be additional 5 pound. There'll be additional 5 pound to the 15.4. So that was step number 8. Step number 9, it says consider ponding instability. It does not apply here. The spec says right there, it says if your slope is less than 1/4 inch per foot, ours is 1/2 inch per foot. So we're good right there. Then step number 10, there. Step number 10, existing roof, and that doesn't apply either. So there is our answer. Is I'm going to go ahead and you see the final result right there, which is, let me get to it right here. If the catch is that, and we have the unbalance of straight going across on the leeward side, I mean the windward side, 4.6 pounds per square foot. And then on a drift, we have 47 feet, which is a 15.4 plus 12.2 of 27.6 pounds per square foot. And also on the leeward side, a uniform load of 15.4 pounds per square foot. Then the balance, we have 20.4, and that 20.4 is what? We have additional 5 pounds of rain, so brought it up to 20.4 pounds per square foot. Good. Okay, so this is how we do the snow load. I hope you liked it. I hope you learned something from it. Your assignment is do the same exact problem over again. Instead of St. Louis, let's go to someplace colder like Massachusetts. Go to Boston. Okay, let's choose Boston. That's where I teach. And use the CMR 780, which is a local code for Massachusetts, and they have all the stuff laid out so you can find the ground snow load right there and do this calculation over again. I hope you like what I did, and if you did, please subscribe to my channel. We see you next time when I do the wind load. Then we come back and do ice load, and then we go to earthquake. That's my plan, and be well and take care of yourself.